There are two general classifications of corrosion which cover most of the specific forms. These are direct chemical attack and electrochemical attack. In both types of corrosion, the metal is converted into a metallic compound such as an oxide, hydroxide, or sulfate. The corrosion process always involves two simultaneous changes. The metal that is attacked or oxidized suffered what may be called anodic change, and the corrosive agent is reduced and may be considered as undergoing cathodic change. The four conditions that must exist before corrosion can occur are the presence of a metal that will corrode, the anode, the presence of a dissimilar conductive materials, the cathode, which has less tendency to corrode, presence of a conductive liquid, the electrolyte, electrical contact between the anode and cathode. This illustration helps to illustrate this. Rust or corrosion that occurs with most metals is a result of the tendency for metals to return to their natural state. Noble metals like gold and platinum do not corrode since they are chemically uncombined in their natural state. It is very important to observe how metals are compatible and incompatible. In other words, dissimilar metal contacts that will result in electrolytic corrosion. This figure illustrates contacting metals and the dissimilar contacting metals. Intergranular corrosion is an attack on or adjacent to the grain boundaries of a metal or alloy. A highly magnified cross-section of most commercial alloys will show its granular structure. This structure consists of quantities of individual grains, and each of these tiny grains has a clearly defined boundary that chemically differs from the metal within the grain center. Heat treatment or stainless steels and aluminum alloys accentuates this problem. Exfoliation of carbon steel is apparent in the channel on the coating exposure panel on the right. The expansion of the metal caused by exfoliation corrosion can create stresses that bend or break connections and lead to structural failure. Uniform, or sometimes called general corrosion. The surface effect produced by the most direct chemical attacks is a uniform etching of the metal. The facilities shown in the picture at the right show how this corrosion can progress if control measures are not taken. Galvanic corrosion is an electrochemical action of two dissimilar metals in the presence of an electrolyte and an electron conductive path. It occurs when dissimilar metals are in contact. Concentration cell corrosion occurs when two or more areas of a metal surface are in contact with different concentrations of the same solution. There are three general types of concentration cell corrosion: metal ion concentration cell, oxygen concentration cell, and active passive cells. Pitting corrosion. Pitting corrosion is localized corrosion that occurs at microscopic defects on the metal surface. The pits are often found underneath surface deposits caused by corrosion product accumulation. The rust bubbles or tubercles on the cast iron indicate that pitting is occurring. Researchers have found that the environment inside the rust bubbles is almost always higher in chlorides and lower in pH, which means it's more acidic than the overall external environment. This leads to concentrated attack inside the pits. Crevice or contact corrosion is the corrosion produced at the region of contact of metals with metals or metals with nonmetals. It may occur at washers, under barnacles, at sand grains, under applied protective films, and at pockets formed by threaded joints. Filiform corrosion. This type of corrosion occurs on painted or plated surfaces when moisture permeates the coating. Long branching filaments of corrosion extend out from the original corrosion pit and cause degradation of the protective coating. This picture shows filiform corrosion causing bleed-through on a welded tank. Stress corrosion cracking. Stress corrosion cracking is caused by the simultaneous effects of tensile stress and specific corrosive environment. Stresses may be due to applied loads, residual stresses from the manufacturing process, or a combination of both. Corrosion fatigue is a special case of stress corrosion caused by the combined effects of cyclic stress and corrosion. No metal is immune from some reduction of its resistance to cyclic stressing if the metal is in a corrosive environment. The beach marks on the propeller shown mark the progression of fatigue on this surface. Fretting corrosion. The rapid corrosion that occurs at the interface between contacting highly loaded metal surfaces when subjected to slight vibratory motion. This type of corrosion is most common in bearing surfaces in machinery such as connecting rods, spline shafts, and bearing supports, and often causes a fatigue failure. Fretting corrosion is greatly retarded when the contacting surfaces can be well lubricated as in machinery bearing surfaces so as to exclude direct contact with air. Erosion corrosion is a result of a combination of an aggressive chemical environment and high fluid surface velocities. This can be the result of fast fluid flow past a stationary object, such as the case with this oil-filled check valve. De-alloying is a rare form of corrosion found in copper alloys, gray cast iron, and some other alloys. De-alloying occurs when the alloy loses the active component of the metal and retains the more corrosion-resistant component in a porous sponge on the metal surface. This photo shows a layer of copper on a surface of a de-alloyed 70% copper, 30% nickel, copper-nickel heat exchanger tube removed from a ship. Stagnant seawater is so corrosive that even the normally corrosive-resistant alloy has corroded. Virtually all copper alloys are subject to de-alloying in some environments. Corrosion in concrete. Concrete is a widely used structural material that is frequently reinforced with carbon steel reinforcing rods, post-tensioning cable, or pre-stressing wires. The steel is necessary to maintain the strength of the structure, but it is subject to corrosion. Microbial corrosion is caused by the presence and activities of microbes. This corrosion can take many forms and can be controlled by biocides or by conventional corrosion control methods. MIC can be a serious problem in stagnant water systems such as the fire protection system that produced the pits shown in the picture.